For over 100 years, our entire picture of the universe has been built on one single foundational idea, that it's expanding. But what if it's not? What if the cracks we're starting to see in our best cosmological models aren't just small issues, but a sign that the whole foundation is wrong?
Think about it, the redshift of distant galaxies, the afterglow of the Big Bang. All these huge pieces of evidence are seen through the lens of an expanding universe. But what if that's just our interpretation? What if there's another way to explain what we're seeing? What if the universe isn't expanding at all?
So, before we can even entertain such a wild idea, we have to look at the reigning champion of cosmology, the Standard Model. And, well, like any champion, it's got some puzzles. Some things it just can't quite explain. Now, the Lambda CDM model, that's our current best guess. It's been incredibly successful. It tells a great story, the universe kicks off with a big bang, and it's been expanding ever since. And to make it all work, we need two very mysterious things: dark matter, which gives us some extra gravity, and dark energy, this bizarre force that's supposedly making the expansion speed up. It explains a lot, for sure, but it is far from a complete picture. And lately, the cracks in the model have been getting bigger. We have what's called the Hubble constant tension, which is a fancy way of saying our two best methods for measuring the universe's expansion rate give us two different answers. That's a huge problem. But the real shocker? That's coming from the James Webb Space Telescope. It's finding these ancient galaxies that are, well, they're impossibly big and grown up for their age. Our current model says they just shouldn't be there. These kinds of anomalies are exactly what drives science forward. They force us to look for new ideas. So let's do that. Let's explore a completely different picture of the universe, one that's radically static. Instead of just trying to patch up the old model, let's ask a much bigger question. What if these aren't just glitches? What if they're symptoms of a fundamentally flawed idea? What if the problem is the core assumption itself, this idea that the fabric of space is stretching? So this brings me to an alternative model that I've been working on, which I call the Dilational Flooding Model, or DFM for short. In this picture, the universe is static and infinite. It isn't going anywhere. So where does redshift come from? Well, it comes from time itself. As we look out into the cosmos, our observational bubble, our light cone, gets bigger and bigger. As it expands, more of the infinite universe, more mass and gravity floods into our view. And that is what creates the effect we've been calling expansion. This right here, this is the absolute key. Space itself isn't stretching. Our view of it is. As our light cone grows, it just keeps encompassing more and more of an already existing, static, infinite universe. It's this dilational flooding of mass into our observable horizon that slows down time and stretches light, creating the redshift we've been misinterpreting for a century. Okay, so how does this actually work? How can an expanding view in a totally static universe produce the exact same redshift we see? The answer, it turns out, is all about the beautiful dance between time, light, and gravity. Let's use an analogy. Imagine a photon of light is like a little boat crossing a huge ocean to get to us. As it travels, the ocean under it gets deeper and deeper. That's our light cone expanding, taking in more mass. This growing depth, the increasing gravitational potential, starts to stretch the boat itself. So by the time it reaches us on the shore, the boat is much longer than when it started its journey. That's what's happening to the photon. Its wavelength gets stretched by this cumulative time dilation, not by stretching space. Now, this isn't just a nice story. It's all grounded in the math of general relativity. And I know equations can look a little scary, but don't worry about the details here. The key takeaway is that this formula gives us a precise way to calculate how that flooding of mass into our light cone actually slows down time. This time dilation is the engine that drives everything in the DFM. All right, so a cool idea is one thing, but does it actually work? Does it hold up when you compare it to real-world data? This is where it gets really, really exciting. Okay, so in the Standard Model, dark energy is described by this thing called the cosmological constant. The problem, to match our observations, that number has to be fine-tuned to an insane degree. It's like trying to balance a pencil on its sharpest point forever. But in my dilatational flooding model, a value for this constant just pops out of the theory naturally. No fine-tuning needed. And here's the kicker. That predicted value matches what we've actually observed to within 3%. So what about that massive JWST problem? Let's take a look. This table compares the distances to a couple of objects. For something relatively close, the two models are pretty similar. But look at that super distant galaxy, one of the oldest things we've ever seen. The DFM says it took less time for its light to reach us. Now, that might not seem like a big difference, but cosmologically speaking, it changes, well, everything. And that shorter travel time is the whole solution. It means the galaxy is actually older than we thought. It had hundreds of millions of extra years to build up, to form stars, to mature. And just like that, the impossibly large galaxies that JWST is seeing are no longer impossible. In fact, they're exactly what this model would predict. So if this model holds up, the implications are just huge. It's not about fixing a few little puzzles. It's about completely rewriting our inventory of what the universe is made of. Just look at this comparison. Metric expansion, the whole idea of space stretching, gone. Don't need it. Dark energy, that mysterious force pushing everything apart, gone. Don't need that either. And cosmic inflation, that hypothetical super fast expansion right after the Big Bang, also gone. With a single, simple shift in perspective, we might be able to get rid of some of the most bizarre and speculative parts of modern cosmology. And I want to be clear, this isn't just some fun thought experiment. The DFM is a real, viable, testable scientific model. It makes very specific predictions that are different from the standard model, predictions about things we can actually go out and measure with our telescopes. This is a serious alternative that deserves a serious look. So I'll leave you with this final thought. For our entire lives, we've been told we live in a dynamic, expanding universe. But what if all that motion we thought we were seeing wasn't in the universe itself, but in our own ever-growing view of it? Could it be that the true nature of the cosmos isn't frantic expansion, but a vast, infinite, and deeply profound stillness?